but I just want to finish the remaining portion of chapter 3 that we want to do. Of course, there is a long bit of chapter 3 which we are not doing, namely that connected dimension 1 algebraic groups are either GM or GA. Must be either GM or GA. That is a theorem, but which we are not doing. So here is this bit of this last bit, which is probably not emphasized so much in, which doesn't come up so much until chapter 6, until how far we were going. But later on and in actual applications, this is, these concepts are very important. Okay, so let V be an affine variety. So I will finish in about 10 minutes or so, and then we can answer questions. Affine T variety, T a torus. By that we mean, of course, T is an algebraic, linear algebraic group, and we know the notion of a variety. As usual, X is equal to character group of T. Then you can write, so what do we mean by KV? Of course, this is the ring of functions. This is a locally finite representation of T. Locally finite rational representation of T. Right? So this is equal to, but every representation, or every, what did we say, every finite dimensional representation splits as a sum of one dimensional representations. So using that, you can write this as where such that T acting on F is equal to chi T acting on F. This definition. So observe that the above is a gradation of KV. What we mean is the following. So you're probably familiar with graded rings, right? Polynomial rings are graded rings. What are they graded by? They're graded by a semigroup, right? Gradations are normally, it's the, in the polynomial ring case, it is graded by the natural numbers in non-negative integers, right? Of course, you could take k, x, y in two variables, and you can keep track of the degree in x and degree in y independently, in which case the gradation will be on n cross n, or 0, 1, 2, infinity cross 0, 1, 2, dot, dot, dot. Okay, so it will be in, so that's a semigroup, right? What are the properties of this gradation? So it is a direct sum over all these graded pieces. That's one property. Second property is that if I take something belonging to some grade, and that grade is denoted by a element of the abelian semigroup. Semigroup just means you can, there is no inverse, that's all, you can't invert necessarily. So, and you take another piece which is graded by another element of the semigroup. If I multiply those two elements, then it is also homogeneous, that is, it belongs to a certain graded piece, and the degree of that or the grade of that is the sum of the grades of the factors, right? So you can generalize this. Gradation just means gradation over a semi-group means that if you have a ring, it can be written as a direct sum over. So this direct sum is in the algebraic sense. So every element of the ring is a finite sum of things belonging to this. So in this sum, almost all, in any given sum, almost all of them are 0. So you can do that. Furthermore, when I take one grade, take the homogeneous piece of the ring belonging to one grade, homogeneous piece of the ring belonging to another grade, I multiply the two, I get into the grade which is the sum of the two of the factors. So in other words, that is k v chi, k v say chi 1 and chi 2 is contained in okay, this is what a gradation means, right? And it is easy to check that if I have f, and so if I have f1, f2, so what do we have to check? So T of this, T acts as an algebra automorphism. So this is equal to T of f1, T of f2, because T acts as an algebra automorphism, and T of f1 is chi t1 of f1, chi 1 t of f1. This is chi, so this is equal to chi 1 t of f1 times chi 2 t of f2. This is equal to chi 1 plus chi 2. So this is chi 1 t times chi 2 t, but that's exactly what we mean by chi 1 plus chi 2 t. So that's an easy check. Right. So there is a natural grading on the T grading, a chi T grading, where chi T is the character group of T on the ring of functions on any affine T variety. Right. Okay. Okay. Now here is one more definition. Like I said, it's intuitively very nice, and you should think of this intuitively, maybe even think of complex numbers and draw pictures. We are going to talk about limits, right? We are going to define something called limit. It is defined algebraically, but it corresponds to the intuitive notion that all of us have from calculus, inherit from there, and you are welcome to think about it that way. But also notice that that is the same thing as what we are doing, and it's quite important in applications, this notion. Okay. So it's very strange, on the one hand you are talking about limits in a algebraic geometry course, but it's quite easy to define. So we say let V be a T variety, let lambda be a one parameter subgroup of T. So have we used that word yet? One parameter subgroup. So this starts for one parameter subgroup. This is nothing, no big deal. It's easy to define. I'll just define it. That's the terminology that is used, for example, in Lie groups. One parameter. All this means is you have a map So one parameter subgroups of a group I am defining is just this set is just Hom of an algebraic group is Hom as algebraic groups of Gm to G. This is the definition. So you should imagine some group like this. If you picture, so one parameter group is, if this is your G, the one parameter subgroup is something like that. Okay. So let y, okay, let's also introduce some notation. Y of G. So what is x? So there is a y and there is an x. What is x of G? Is the character group of, can I say character group of G? Yeah, indeed I can say character group of G, right? Y of G is co-character, which is the same as a one parameter subgroup group of G. Let's see if this makes sense. So this is, so I have two one parameter subgroups. I claim I can multiply them and get another one parameter subgroup, right? So if lambda is a homomorphism from G, lambda 1 is a homomorphism from Gm to G, lambda 2 is another homomorphism from Gm to G. How do I get lambda 1 plus lambda 2? Right? That's how I want to denote it additively, just like in the character group case. I want it to go from Gm to G. Right? So the natural thing to do is you take lambda Gm cross Gm to G cross G to G. You put mu here, you put lambda 1 cross lambda 2 here, and you get a, that's a group homomorphism, right? Because it's a, I have factored it as products of two group homomorphisms.
But this is not commutative. Lambda 1 plus lambda 2 is not lambda 2 plus.
Aha, okay. So you're right. So, okay. Correct, absolutely. So I can't write it additively. Okay, so let's assume that G is diagonalizable. G is commutative. Okay, now what else do we want to say? And there is also, so this makes it into an abelian group that I can write additively. I mean, it's a commutative group that I can make additively, and as Abhishek correctly points out, this should be, I'm assuming G is commutative. Okay. Okay. Now, so there is a pairing. So X is the character group of G, Y is the co-character group of G. Then we get a natural pairing as follows. So given chi, so chi is notation for the character. lambda is notation for the co-character. These are standard notation. So when you write lambda, it means one parameter subgroup. When you write a chi, that means a character. Okay, so this is should get used to that notation. So what is chi? Chi goes from GM to, sorry, lambda goes from GM to G. Chi goes from G to GM. So finally I get an homomorphism from GM to GM. But what are homomorphisms from GM to GM? So homomorphisms from GM to GM are nothing but Z. So T, that power T going to some T power N, and that is the element of Z. So this is, so the so that is this mapping. So I will just write it out. So this defines the composition. So the composition defines an element of so you get a pairing just this map. And let's see in what context he says it. It's a, if you have a torus, it's a perfect pairing. So let's say this. Okay, so comment. Even if G is not commutative, on X star G or YG, we still have multiplication by integers. Let's understand this. So what he means by that, I suppose, is that, okay, let's just think. Can I make Y star G into a, is it clear that Y star G is a group? I mean, YG is a group?
We are not saying, I think we are not saying that YG is a group in this case.
I don't know why he writes this, because he is writing this, he wants to write this as a structure of an abelian group. He wants to, he somehow has, this is what he has, but I am thinking, why not make this into a group itself? So does this define a multiplication on the structure on Y star G and X lower star G, Y of G?
If lambda 1 is equal to lambda 2, then that is what he is saying.
Yes, that's what he's trying to say. But can't we generalize this is what I'm asking. Let's see. I can't call it lambda 1 plus lambda 2, but let me call it lambda 1 times lambda 2. Let me write it multiplicatively. Okay. So would it be all right? What would be the inverse of
G inverse. Sending G to H.
so so lambda 1 inverse, I can write lambda 1 inverse, right? And what would be identity is the trivial map. So it looks all right to me. Okay. In any case, okay. So we end up using this very much in the case of a torus, right? When there is no problem. But he makes this comment. But even more generally, it has more structure on it. So what he means is this is like lambda 1 to the n. You can still talk about lambda 1 to the n. That's all he means. So he's thinking of it still additively. You can't write lambda 1 plus lambda 2, but you can write lambda 1 to the n. That's what he means. Okay, let's see if there is any. Okay, so here is a lemma. Let's do this. So T torus. So this is T torus. So any homomorphism from X to Z is of the form. Okay, so with the above notation, X cross Y to Z is a perfect pair. That is, any homomorphism from X to Z, this is an abelian group homomorphism, is of the form chi going to chi lambda for some lambda in Y, and similarly for Y. So in particular, Y is a free abelian group. To the map A tensor lambda to lambda A defines a canonical homomorphism of abelian groups K star canonical isomorphism. See, T is a diagonalizable subgroup, which means it's isomorphic to some dn. I mean, it's more than being diagonalizable, it is isomorphic to some dn. That's our definition of what a torus is. This gives a canonical isomorphism. It's an isomorphism that is free of. See, if you think of this as an abelian group, this is Z cross Z direction. This is a group homomorphism, group isomorphism. So this is Z plus Z plus Z. So what is this going to be? K star cross K star. K star direct sum, K star direct sum, right? So this gives, as a group, T is, this gives a canonical, independent of choices of coordinates. Okay, that's the claim there. Okay. Okay, so I think this proof is among those that are best left to the reader. So I'm just not going to try and prove this, rather continue with continue from here. Okay, so
pairing x cross y to z. So what kind of map is that? I mean,
it's a,
given any chi and lambda, I can see how you get that element of z.
yes.
But
What is a map? What kind of a?
I mean,
It's a bilinear. If you think of it as Z modules, it's a bilinear map. X and Y are abelian groups, therefore they are Z modules. So it is like a bilinear form. I mean, not form because it's not on the same space, but X cross, it's bilinear, it's bi-additive. It's a notion of a bilinear form, except that it is not over a vector space but over Z.
in that statement you're making x to z is a group homomorphism.
Is a group homomorphism, yes. So any abelian group homomorphism, yes. X is an it's an abelian group. So X to Z is of the form. This what it means to say it's a perfect pairing. Okay, what this amounts to is that Y is equal to, so there is a, once you have a pairing, see this is you might have seen this in vector spaces too. So if I have V cross W to K, if this is a perfect pairing, then W can be identified with V star. Right? How do I take W to V star? Then, so if this is perfect, if this is a bilinear map which is perfect, is a perfect pairing, then W is equal to V star. How you can, so so there is a map from W to V star given by W going to the map this is the map, and it takes V. So if you denote this map by V to VW, right? And why is this 1 1? Because this is a perfect pairing, which means that if I have, so to give meaning to this, so this is 1 1. Why is this 1 1? If this is 0, meaning if so, because VW equal to 0 for all V implies W equals 0. That's one of the things of being perfect, right? Okay, so this map is 1 1. Why is it onto? So that is the part that says every homomorphism comes from, right? So onto, because every so you can say this, okay, so instead of saying it that way, so let's assume V is, I think maybe I should assume V is finite dimensional. Then if I assume the other way, it will come out. For example, so okay, so suppose we have this, right? If V comma W is equal to 0 for all V W in W, then V is equal to 0. Right? What does that mean? That means you have a map from V to W star, right, which is 1 1 for the same reason. See, we have proved that this map is 1 1 because of this property. Typically what it said is you are given these two things, that is you know that VW equal to 0 for all V implies W equal to 0, and if the other way, if VW equal to 0 for all W in W, then V is 0. Okay, then by the same token you get a map from V to W star. Okay, 1 1. So far we have not assumed anything about dimensionality, but now if assume that, so this is assumed, let's assume, so this part, let's assume V and W are finite dimensional. Maybe it's true slightly more generally, but let's not care. Okay, why? Because you have an embedding of V into W star, and you have both embeddings, therefore the dimensions are equal, therefore this map must be a onto map. Okay, so once you have a perfect pairing, this natural map, so once you have a pairing, you have a natural map. Once you have this map is 1 1. Once you have the other way, you have this map will become onto, if you want, if you wish, because once you have this, then this becomes a 1 1 map. Therefore the dimension of this is at most the dimension of this. Therefore, this becomes an onto map. Right? Yes.
Reason subjectivity because every map is of the form inner product of that comma W.
So that
That is how you define it
is
in the technical concept.
right here. See, in the finite dimensional case, you can say this way or that way. Okay. So typically, when you say a bilinear form is non-degenerate, how do you say it? You only say it this way. If I fix a V for all W, if it is 0, then this V is 0, and the other way. if I fix something here for all this, it is 0, then this is 0. Okay, that's a natural thing to say because you are doing everything in terms of, right? So in any case, here it is finite. This is a finite finitely generated thing. So a similar thing will be true for because it's all things are finitely generated here. Is that?
And this state is defined to be Hom VK, right?
Hom VK, yes.
So every map from V to K is of the form inner product that comma W. So it will be surjective.
But we are not assuming.
No, without this property, you mean?
No. Yeah, means because of that.
Say that again.
Any homomorphism from V to K is of the form inner product that comma W.
Why is that?
That is the definition of perfect pairing. So we are assuming it to be perfect pairing.
Okay, so because you are saying I'm giving you this definition. Okay, fine. Okay, fine. Right, but I went back one step, and normally perfect pairings are not defined that way. Correct, absolutely. Perfect pairings are defined like this. These two conditions. These are much more natural. Right? So, right, and in that case, in fact, this follows because because of the argument idea. All right. So, I mean, there is an independent definition. In particular, this is true. This one. Okay. Is that all right? Okay. Okay, so let's go on here. So here is the interesting thing. So you can define, so we say given V in B, so this is V is a T variety, we say limit T goes to 0 of lambda T V exists. So this is a definition, right? If, what is the natural thing to expect? So you have to, this is just notation, and it corresponds, like I said, to your intuitive notion of limit, but we have to define it algebraically in terms of varieties and maps, etc. So what is the natural thing? So you have a map GM to T. This is the lambda map, and you have a map from this to V by T going to TV. This is the orbit map. Every element T just goes to the right. So this is the orbit of V. So let me write OV. Okay. So this is, so you have this map, right? This is this map, lambda TV. T goes to lambda TV. Okay. So let me use T here. Let me use X here because X goes to XV here, or G goes to GV. That's better. T I am using for a parameter. So this goes to lambda of T. Lambda T is an element of T. Okay. Now, exists if, see, this is sitting inside A1, right? This is K star and this is K, right? If this map is the restriction of a map, if I have a map from a subspace, subvariety, or more generally subset, so this subset is naturally sitting in a bigger set, I say the limit exists when the map of that subset is actually the restriction of an honest map from the bigger one, and I call the extension, the extra point, there is only one extra point there, right? and the image of that extra point to be the limit of this one. Simple enough, right? If the map T going to lambda TV from GM to V extends to A1, extends meaning not in any sense, is the, if you want more, if you are psychologically more comfortable, is the restriction of a map from A1 to V, right? And we say, so the extends to a map lambda, let's call it, should we call it lambda tilde, that extends to a map from A1 to V. We write limit T goes to is equal to that extension evaluated at 0. Right? And the extension, that makes sense because the extension is unique. Why is the extension unique?
Because on dense subsets they go.
Because this is a continuous map and that's a dense subset. Right. In particular case. So the extension is unique if it exists. It need not exist in every case. Right? And so the above makes sense. So you might just say this limit exists or this limit does not exist and what it is informally, right? Just it exists if, I mean, you'll say this is equal to does not exist, which means that does not exist, etc. Clear? So what would, now question, similarly for limit t tending to infinity of lambda t. Now what do we do?
Look at T1, G electrospecific, GM to GM, 1 T going x going to 1 by x.
Right, exactly. Right? It's just like in complex analysis when you want to say something is happening at infinity, you get around from the, by just saying you put 1 over z and take limit as z goes to z. Right? It's the same idea. So you take lambda inverse, right? You take lambda inverse, and so this is defined. So similarly, in fact, this is defined as nothing but limit t going to 0 of lambda inverse t. So it exists when that exists, it is, and it's equal to that, right? Okay. So here is lemma. V is a T variety, a fine T variety. Then lambda is a one parameter subgroup of T. So co-character, one parameter subgroup, all these are equivalent terms, right? One parameter subgroup of T. Then V in V such that limit T goes to 0 of lambda TB exists, right? is a closed sub of V, is closed in V. So it's a closed subvariety. Okay. You might want to compute it in, think of some natural T varieties. For example, T could be a torus sitting inside a group and you have a conjugation action, right? So that makes the group, for example, GLN, take the diagonal group of diagonal matrices, that's a torus sitting inside GLN, right? Now you can take the conjugation action of that. So G becomes a T variety. Take a lambda. What is this? Right? So that just in that context, it's very important to understand that. Just in the context that I mentioned, in this very specific context, G is, and it's among the exercises at the end. G is GLN, T is a maximal torus. You just take it to be the diagonal elements. Take a one parameter subgroup. What is this? In terms of the one parameter subgroup, right? And what is that one parameter subgroup? It is easy to describe. You have T, although it's very hands-on. You have T. It's a map from GM to T, right? And if you keep on projecting to each of the coordinates, if you concentrate just on one entry, it is just another GM. So it's a map from GM to GM, which means that it's just defined by an integer. So that is, this T goes to T to something, some integer power, next T to some other integer power. So this one parameter subgroup is just a bunch of integers. Right? So in terms of those integers, suppose I give you 1, 2, 3, 4, 5, n, or 20, 35, or some other set of integers. What is this? And it's going to be a subgroup in that case. It's easy. That is trivial. The fact that it is a subgroup is rather trivial. Okay, it's immediate from the definitions. So what is that closed subgroup? Right, that's an important problem, and if you have understood that already is something that you can take away from this course. Okay, particularly because it comes up in applications in, for example, if I don't know, many of you may be doing geometric invariant theory or whatever courses there, where this is very important. Okay, so first this is A, B, V lambda intersect V minus lambda is the set of fixed points of im lambda, that is V in V such that lambda T of V is equal to V for all T in K. Okay, so let me write down the example before giving the proof. The proof is, we'll just write down what the idea is. It's the kind of thing again that probably I am not good at explaining, but perhaps nobody is, because the book just writes down something and expects you to decipher it yourself. Okay. Example. G is an arbitrary linear algebraic group. Lambda GM to G, a co-character. So we let P lambda So this is the notation for V lambda in this case. This is just going to be this V. Okay, I didn't define this. So this is V lambda. That's P lambda in this case. So what is it? It is all G in G such that limit T goes to 0 of lambda T acting on G. So this is, when I write it on top here, it means conjugation exists. So it is immediate that this is a closed. So it's immediate. So this is clearly a subgroup. Why? Because if it exists for G and it exists for H, it exists for GH. It just takes it to the product of the limits, right? So it's clear that it's a subgroup. It is closed by the lemma. And P lambda intersect P minus lambda is the centralizer of. So it is those that are fixed by this, and that's centralizer of lambda, image of lambda. Right, so let's just see what the proof is. Okay, the proof consists of, here is the idea. In fact, you identify it's closed, right? What is a closed subset of an affine variety? It's given by the loci of certain equations. You identify that set of equations. That's the proof. Okay? And it's done very beautifully. Of course, it's just one line. I mean, I will write down that one line. It's so proof. So you think of, so this KV we had. So let me write down the idea. Idea is to write down, is to identify the functions, the ideal of V lambda. That's the idea. Right, and it's very naturally identified. Once you write it, it seems intuitively, what else could it have been? Right? And the idea is follows. So you write this. Right, we have that. So every function is breaks up into these eigenspaces for T. So now, so let me take a function f. So I want to identify those. I will identify it in terms of this decomposition of that. Okay. So I write this as right. F chi is the component of f belonging to that vector, that subspace, that eigenspace. Okay. Now, so let's see. right? I've just but how does lambda, so what does it mean? Let's think of this. Okay, this is just the, what does f chi mean? T acting on, sorry, I'm using T also for the element of the torus, I'm using T also for the element of the GM, so it could be a little, let's use G for a minute. G f chi is equal to chi G f chi. That's what it means to be an eigen vector. Okay, so this is the same as, so let's think of this. This is the same as chi of lambda of T f chi, right? But what is this? This is, in other words, it's T of chi of lambda of f chi. Correct? Okay. Now, if t as t goes to 0, all this has to make sense, right? If as t goes to 0, I mean, of course there is a v, I'm going to apply it to a certain v, and then all of this will have to make sense as I take limit as t goes to 0. Now, when will this make sense as t goes to 0? If this is positive, it is not a problem. It will make sense. But if it is negative, it is not going to make sense. Right? Because you will get some small number, you will take a reciprocal of a small number, I mean intuitively, right? So what should happen? Somehow this should take care of that. In other words, you would want this to be 0 whenever this is negative. So therefore the ideal is all those generated by all those f kv chi's where chi comma lambda is less than 0. That's the identification. Correct? So finally, so v lambda, therefore, so this is the one line that's written. Okay. Okay. Now why this exactly is that? That is for us to check. Okay. V lambda is equal to ideal of is equal to loci of 0 locus of kv chi lambda less than 0. In other words, we have to show that the limit exists if and only if that V satisfies all those functions. It's the 0 locus of those functions. Okay, and the second part is should be rather easy. So let us see. So let's do B. by the way, here I had one more comment to make. So here you might want to note this down. So as I said, P lambda is an important group. So is the following. What is P lambda? It is all those elements of the group for which the conjugation by lambda has a limit. Right? You can ask, when is this limit equal to 1? So the conjugation has a limit is some group. There is a subgroup where this is actually goes to the limit is actually 1, equal to 1 of the group, the linear algebraic group G, right? So that's also an important subgroup. So he doesn't mention this, but it does come up in. So let's call it U lambda, very suggestively, is equal to, continuing this thing you should write, U lambda is G in G, such that limit t goes to 0 of lambda t G is equal to 1. Okay. So clearly this is contained in V lambda intersect V minus lambda, right? If lambda t of V is equal to V for all t, maybe I should have written on top, then surely it exists, both V limit as t goes to 0 exists and limit as t goes to infinity exists, both are equal to V. Now why is the converse, right? Suppose limit as t goes to 0 exists, limit as t goes to infinity exists, then this must be the case. Why? Because what is this? This is, so let's prove 2. So it belongs to 0 means what? V so suppose V belongs to V lambda intersect V minus lambda, then I have to show, then look at lambda t of V. I want to show it's V, so how do I show that? So V, it is 0 on all the so let's see how to show that lambda of t of V is equal to V. Okay, so V lambda is the set of V, so he writes this is equal to the set of V that is annihilated by all V chi right, so there is something to be seen. So this is set of all V in V such that f chi is equal to 0 for all chi lambda not equal to 0 for all f. Right. Let's write it for all f in k v chi such that for all chi such that chi lambda not equal to 0. This is what we have proved. Right? V lambda is the this is the locus of zeros of this, V minus lambda, so it belongs to the locus of this and the locus of zeros of this, which means precisely that it is 0 on all those functions and 0 on all those functions. Right? Okay, that's what it is. And then he says this is the same as set of V with f of lambda tv is equal to f of v for all f in kj. Okay, why is that? Okay, so here is the idea. So now now I finally got it. So let's look at the idea of the proof. If something belongs here, I want to show it has this property. Right? This is what we want to show. To show that, okay, think of this as one point. Think of this as, for some t, think of this as another point. For every t I have to show this, but fix a t for a minute. So this is one point. How do I shoot 2 points at the same and affine variety? I can show all functions evaluated the same. Right? So to show, so let's rewrite the proof. So to show lambda t v is equal to v, enough to show f of lambda t v is equal to f of v for all v in, for all f in kv. Right? But for all f in kv, I can replace it by all kv chi. Okay? So enough to show for all f in kv chi for all chi. Correct? So let's compute this. So this is what lambda t inverse of f of v. Right? So I push this to this side. Correct? Okay. Now, if f belongs to chi, what is this? This is chi of so now for v, okay, so I have written it like this. Right? But that is same as okay, chi of lambda t inverse of f of v. Now this is a scalar in front, is equal to f of v for all f in kv chi, for all chi in chi x. This is what we want. Okay. Now I claim this is okay because right, so f of v equal to 0, but f of v equal to 0 unless chi lambda t inverse equal to, so unless chi lambda is equal to 0, in which case chi lambda t inverse is equal to 1. What is this? This is t of minus chi lambda. Correct? So you've written this is what we want to show. Either this is 0 or this is 1. So you
So actually that is actually bilinear, so you can pull the minus out and
where
so
say that again,
that pairing is bilinear.
yes,
Chi comma, no, I'm just asking you. Chi comma minus lambda is minus chi comma lambda. Okay, it's not in this proof. I'm just asking in general, the pairing chi comma lambda. That is bilinear, right?
that's bilinear, yes. That's bilinear, yes. It is bilinear, it's, yes, absolutely. Yeah. Is this all right? So you can scratch this. This is the proof. Okay, so that finishes what I wanted to say. So sorry, it took much longer than what I thought it would take. It always does. Okay, any questions? So we meet at 4 for the exam, but before, any quick questions you might have, even if they are not related to the exam.
You said this. You want to give your group structure to the co-character. Set of
Yes,
co-characters.
yes.
And you said that for G non-abelian.
Yes.
So if you have lambda 1 plus lambda 2.
So you can't write plus lambda 2, it's better not to
lambda
write.
1, lambda 2. You want to make it a co-character again.
Yes.
So you must have lambda 1, lambda 2 of G1, G2 is equal to lambda 1, G1. That is lambda 1,
lambda 2 on T. Because
yeah.
it evaluates it. You can write a G if you wish, but T.
T.
Yeah.
So
that would be defined as lambda 1T times lambda 2T. Or will that be a...
If I...
Yeah.
So okay, I'll just choose.
Yes.
What are the characters of the I can see determinate for n of the characters of here. Are these all the characters?
Yes, they are all the characters.
How do you prove that?
How do you prove that? How do I prove that all the characters? Okay. Okay, it must, so roughly it goes like this. So if you have a character, it must be 0 on unipotent, it must be identity on unipotent element.
It must be.
identity on a unipotent element, right? Because where will a unipotent element go? It has to go to a unipotent element of the image, but there is only one. Okay. And then you can try to show that so on all the subgroup generated by unipotent elements, it is trivial. You can try to show that that's a very large subgroup. Just try it for GL2. Try to see what the subgroup of generated by unipotent elements is. Okay. So, for example, you can try 1, 1, x and 1, 1, y, and try to see the group generated by them. Let me see if let me think of after you think, there must be pretty easy proof, but it requires after you think, after some thought. But that's a good question. Yes.
Is it possible to somehow give the quotient group an algebraic group structure if G is a linear algebraic group?
That is
Are there some conditions on normal subgroup so that G mod N is a linear algebraic group?
That's a very good question. What we will do is that if G is a linear algebraic group and H is a closed subgroup, then G mod H has the structure of a variety. Not necessarily affine, but it has the structure of a variety, and that's quite hard to prove. We'll do that in chapter 5. So, quotient constructions are not easy in algebraic geometry. So, in particular, the question that you ask will be, so in general we'll show that if H is a closed subgroup, G mod H is a variety. So if N is a normal subgroup, in particular N normal subgroup which is closed, G mod N is a group as well as a variety, in which case the variety structure is affine and it will also be an affine linear algebraic group in its own right. So indeed it's natural to expect that, but quite hard to prove. So we will do that. Hopefully we get that far.
If I have a injective morphism of diagonalizable groups G to H, then the induced map on characters will be surjective.
If you have injective map of diagonalizable groups.
Next, the induced morphism on the character groups will be surjective.
Okay, how do you prove this is the question. Okay, so G and H said. So you can think of this as a sum of this, closed sum of that, because the image under homomorphism is closed. So
why is this surjective?
I have
an injective morphism of varieties, but image is also closed. But I don't see why is it an isomorphism of varieties.
No, it is not an isomorphism of varieties.
Onto its image. But onto its image also.
KH to KG is an onto map.
Why?
y. So if you have an affine variety and a closed subvariety, any function on the closed subvariety can be extended to the affine variety. In general. Is that okay? Let's see if that.
Why is the map from KH to KG surjective?
Because kg, what is kg? Kg is the functions on that closed subvariety.
So you are identifying G with the image.
Yes.
But it will not be an isomorphism of varieties.
So it's just an injective homomorphism, you're saying?
Homomorphism of varieties.
Okay, injective homomorphism of varieties. Okay, fine. So then injective homomorphism, you want to say that say that again? On the K, chi H2, so you want to say chi. This is what you want to ask. Okay, let's see. So let's say no, it's not true. It's not true for the same reason that you said. So here is one example. Suppose I take GM to
G and H are diagonal as well.
take GM to GM in characteristic 2 and take T to T square.
Yeah, I thought of that.
You must be, which chapter is this? Is this from the book?
Yeah, diagonal.
Which one?
Page 46.
36, huh?
Page 46.
Okay.
Number 2. 3.2.10 number 2.
If phi is injective, so let's give a counter example. Let's see. So if I think of phi GM to GM, so K equals K bar, characteristic K equals 2, and T going to T square. This is an injective map. Yes. And what is it on the, so chi of GM is Z, Z, 1 goes to 2, right? So I guess that's wrong. I can't agree, at least. Good, I didn't want to say it. It seems to be wrong. Good. So, think about it. I will also think about it, but looks like he made a mistake. Oh, I thought the mistakes were only in the second half. Okay. Good point, thanks. By the way, also your question, did you try that? Why is that reduced?
The
Book gives a different, okay, I also noticed it in the book. Did you understand the proof?
yeah.
Yeah, okay.
For sure, the ideally considers as more T power D. I mean, Km is Kt more T power D minus 1, right? That is that.
Okay, for the benefit of all of us, so let's recall the question and the proof and the thing in the book. I don't know why we didn't think of that. That's a simple way of doing it. So it's all right? Now you understand. Okay, what's the thing? So we had to show that T is we were reduced to this situation. So where T is a finite abelian group. Without p torsion. So characteristic K of K equal to P bigger than 0. Show K T, this is the group ring, is reduced. This is the problem, and here is the solution the book gives. So write T, so any finite group is a sum of cyclic, you can write it as a product of cyclic groups. So So what is KT therefore? Is KT1 tensor KT2 etc. Right? So the claim is that I want to show that this is a product of fields. It's enough to show that each one is a product of fields. So claim KT is a morphic to that, enough to show so may assume T is cyclic, and then KT becomes cyclic and okay, so D is equal to order of T. So if this is a product of fields, this is a product of fields. Tensor, you will get K tensor K tensor K. So for example, if the first one is a product of two fields, which you can write like this, and the second one is a product of three fields, say, and then you get K tensor K, K tensor K, and but K tensor K is K. Okay, is that? And D is order of T. Note P does not divide D. Therefore, this XD minus 1, so it has distinct roots. So, because if you wish, the derivative of this is it and its R co-prime exactly. So XD minus 1 has distinct roots in K. K equal to K bar, so it has all the roots there. I mean, in any case, over the algebraic closure, it has distinct roots. So it's a product of fields. Any other questions?
Let lambda 1, lambda 2
Yes.
of T1, T2.
Yes.
That will be lambda 1 of T1, T2 into lambda 2 of T1, T2.
Lambda 1, lambda 2 of T.
No, yeah, lambda 1, lambda 2 is the
So, okay, so lambda 1,
lambda 2.
so lambda 1 and lambda 2 are one parameter subgroups. So, lambda 1, lambda 2 of T,
No, I'm saying that T1, T2. So suppose take two, T1 and T2.
take T1 and T2.
So I want this, if this has
Aha, so you are saying it will be a problem?
this will be problem.
Ah, okay, it will be a problem. Okay, good. So, lambda 1 of, okay, thanks. So, we want to check whether this is lambda 1 of T1, T2 times lambda 2 of T1, T2.
No. Check that
Lambda 1, lambda 2 of T1
yeah.
times lambda 1, lambda 2 of T2. Okay, this will be a problem. Why? Because
By definition,
Just
this will correct. So, this will be what? Lambda 1 T1, lambda 2 T2, and this is lambda. Indeed. Thank you. Yeah, so that will be a problem. So, he is pointing out that if G, okay, but let us see. Okay, so we should be careful when we try to extend beyond the book. So, but let us check that. Could you check that at least what the book says is correct?
That is just lambda power n. So
Yeah,
how was
so-
lambda?
So, lambda power n of T1, T2, his definition is, so let us check that this must be a one parameter subgroup. So, on the one hand it is that how I,
Lambda 2 and lambda 2 complex. Image of
no, wait a second. So, what is my definition of lambda n? Lambda n is lambda n of, by definition, so I define lambda n of T to be lambda T n. That's how I define it. So, this one will be lambda, even that looks like a problem to me.
T1 and T2 commute.
T1 and T2 commute, yes.
Therefore, you have lambda T1, lambda T2 is equal to lambda T2, lambda T1.
Aha, but why couldn't I do that before?
Because you had lambda 1 and lambda 2.
Ah, there you go. Very good. Thank you. One has to be careful, yes. Okay, good. Absolutely. So, let's see. If G is arbitrary, we still have lambda. Okay, so that's okay. Good. Thanks. Yes.
The,
Oh, oh. Oh.
like I can see that the centralizer is a closed subgroup. Why is the normalizer closed? I mean, last time we showed that NGH mod NGH was finite.
Yes. So, why is the normalizer a closed subgroup? So, in general, suppose I have a closed subgroup, why is the normalizer a closed subgroup? Okay, let's see. So, I want to define, so I have a subgroup, I want to define say the ideal of the normalizer, So take a function. Let's maybe he has to go, so let's finish the class, but let's if you have time, I'm willing to think about this. So